Hi, my name is Cecil C. from singaporestudent.com. Thank you for watching my video. Today is Wednesday, 25th of April 2012. The one that I would like to explain to you today is how to draw the second ionization energy graph against the number of proton or against the element in order. Before you continue, you need to do several things. One is to download the empty pattern here, right? I think you find the link next to my the link to this website, the links to this video. You're going to fill up some numbers here, and we are going to draw together. And this is the after you finish, you're going to get something like this, the second ionization energy graph. And we can get it by filling up this table to help you draw the second ionization energy. Inside that file also, you're going to see the computer generated graph. This is of course the correct one. So our answer is only approximation or a rough sketch of this graph. Now we are going to fill up this table together, similar like yesterday. And the first thing you do is to fill up the first row, all these elements from hydrogen to calcium, and all will have a charge of +1. The reason is because this graph is for second ionization energy, which means second ionization energy is involved the cation with +1 charge to produce cation with 2+ charge, because you're taking the second electron from that atom. So you can fill up all these elements, and you might need periodic table to help you with that. The number of proton is of course very easy for you to fill up, because it's in order from 1 for hydrogen and 20 for calcium. The inner electron is the number of electron inside that cation. That is not the valence electron. In the case of H+, you don't have, and you're not going to have the second ionization energy for hydrogen in the first place, because hydrogen have only 1 electron. You cannot take the second electron from H+. So we are going to leave this column empty. How about He+? He have 1 electron, and that electron is considered valence electron. So helium, He+ and Li+ do not have inner electron, because both of them have 1 and 2 electron on the first shell. Be+ on the other hand is having 2 electron on the first shell and 1 electron on the second shell, so the inner electron, we take it as 2, and it will be 2 all the way until Na+, because at Na+, you're having 10 electron, 2 on the first shell and 8 on the second shell. From Mg+ all the way until K+, they will have 10 inner electron 10 in electron. In the case of Mg plus have 11 electron, 10 on the first and second shell, and 1 on the third shell. So the inner electron is counted as 10. In the case of K plus have 18 electron, 10 on first and second shell and 8 on the third shell. In the case of Ca plus, you have 18 electron. Why do we need to fill up this inner electron? Is to help us to find effective nuclear charge for all the elements. And to do that is very simple. You just subtract inner electron from the number of protons, so it's easy for us to do. 2, 3, 4, 5, 6, 7, 8, 9. So it will be increasing from beryllium to Be plus to Na plus. Similar also from Mg plus to K plus, the effective nuclear charge will be increasing. So 2, 3, 4, 5, 6, 7, 8, 9. It will drop again. Ca plus 20 minus 18 is 2. We have finished filling up the first 3 rows: proton, inner electron, and effective nuclear charge. By the way, the second ionization energy is affected by these 3 factors: effective nuclear charge, the number of shell, and the electronic configuration. Later we are going to learn how these 3 factors affect. Number of shell, also quite simple. Helium and lithium have 1 shell only because Li plus have 2 electrons. Initially 3, then becomes 2. In the case of Be plus to Na plus, all of them have 2 shell. Na plus also 2 shell. In the case of magnesium all the way until potassium, they have 3 shell. In the case of Ca plus, is of course it has 4 shell. Very simple. Now my explanation how this thing affect. If you have more electron shell, what happens to the second ionization energy is the ionization energy will be smaller, because ionization energy is a measurement of how difficult or how easy it is for you to remove the electron from that cation. So if you have more shell, then the electron will be further away from the center. So this one, the explanation in the case of shell, if you have a increase of the number of shell, you're going to have a very significant decrease in the second ionization energy. So we mark this with the green arrow. So this green arrow represents a big drop of second ionization energy. So we mark here. So from lithium to beryllium, there will be Li plus to Be plus, there will be a very significant decrease. Same thing happen to from Na plus to Mg plus, there will be a lot of decrease here. And from K plus to Ca plus also there will be a big decrease. So this one, significant decrease. In the case of effective nuclear charge, it also affects. How does it affect the second ionization energy? Effective nuclear charge is a measurement of how strong or how weak the electron is attracted to the nucleus. So the higher effective nuclear charge, the higher the second ionization energy. So we mark here the effective nuclear charge. I'm going to mark the pattern. That means this red arrow here represents a gradual increase of second ionization energy. In this case, Li plus has higher second ionization energy than helium plus. The same pattern is repeated from Be plus to Na plus. The second ionization energy will increase gradually. The same thing happens also from magnesium plus to K plus. So effective nuclear charge here will have the effect of gradually increasing the second ionization energy. So I mark here is gradual increase in second ionization energy. How about the electronic configuration? This thing also affect, even though the effect is not as strong as the number of shell and effective nuclear charge. Because some of these ions, some of these cations have a stable electronic configuration. So when it is stable, the second ionization energy tends to be high because it's difficult for you to remove electron from a stable atom or a stable ion. We don't have space for all the electron. We just fill up the last electron on each cation. So in the case of H plus, you have down here 1s1, Li plus is 1s2, 2s1, 2s2. H plus, of course, you don't have because you already removed the electron. C plus is 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. From Mg plus to Al3 plus is 3s1, 3s2, 3s3, 3s4. For silicon Si plus, it will be 3p1, 3p2, 3p3, 3p4, 3p5, 3p6, and 4s1 is for Ca2 plus. Then we have finished filling up the last row, which is the electronic configuration, and we are going to mark with blue color the ions that are stable. The one that have stable electronic configurations are the one with the full s orbital, or full p orbital, or half full p orbital. So we are going to mark them one by one. Full s orbital, yes. So 1s2, 2s2, 3s2. Full p orbital, 2p6 and 3p6. How about half full p orbital? 2p3 and 3p3. So all these are stable. Li plus, boron plus, O plus, Na plus, and so on. Now, if Li plus is stable, then the next cation after that will have a slight decrease in second ionization energy. So we mark with the one that we mark with blue color here represents a slight decrease. A slight decrease of second ionization energy, right? Small decrease. And we can start drawing now. For small atoms, the second ionization energy is relatively high, so in general, it's going to go down. Usually, I draw with the green color here, the significant decrease. So starting from Li plus, we draw a significant decrease of second ionization energy. Similar things happen from Na plus to Mg plus. Also a significant decrease, so we see that the gradient is very sharp downwards. Also from potassium to K plus to Ca plus. Now, that is the effect of adding more shell. We are going to draw the effect of increasing effective nuclear charge. So we draw a gradual increase from helium plus to lithium plus, and also from beryllium plus all the way to Na plus. So we are going to draw a little bit carbon all the way until oxygen. Then this one. Now, why do I have to split the gradual increase here? Because in the middle here we have the effect of a small decrease because of the electronic configuration. So we are going to draw a slight decrease from boron plus to C plus, also from oxygen plus to chlorine plus. We are going also to draw the same similar pattern from Mg plus to K plus, a slight increase from magnesium to aluminium, gradual increase also from silicon to sulfur, also gradual increase from chlorine to K plus, and there will be a gradual decrease from aluminium to silicon, and also from S plus to Cl plus. So this is how the second ionization energy graph look like. Second ionization. So we have three factors affecting it. Number of shell, the most significant factor. Effective nuclear charge and electronic configuration. You can check your answer with my answer here on the file, and also you can compare it with the second ionization energy graph from the computer generated one. I think that's this is how usually I explain to my students. They so far they understand how to draw second ionization graph. Hopefully this explanation is useful for you. In case you have question, you can contact me also. From my website, you have my phone number 90885633. You can also come to my trial lesson every Saturday in Bukit Batok. Right? So that's all for today. Thank you for watching my explanation. Goodbye.